Okay. Now, you certainly can write this down, but this is the printout I gave you. It's just written real small. Okay. So what we're dealing with here is an electron that is transferred. It's important that you know that this is just another piece of this entire chapter. It's kind of summarized real fast. We've learned precipitate reaction. And we use net ionic rules to try to make them easier. Then we had acid-base reactions, which are called neutralization reactions. And a subset of those were the gas-producing, right? Reactions. Okay? Now, we're going to have redox reactions. Sometimes these things give you redox reactions, but I'm never going to pair them. But what I am going to give you on the test, I'm going to give you 3 or 4 reactions, and you have to write out and balance them. And if it's a precipitate, you have to write out the precipitate and the net ionic. If it's a gas forming, you got to write out the net ionic and the gas and the water. If it's a redox, you have to do what we're going to talk about today. It's just an addition, sort of the same idea we've been doing the entire time. Move this down here. Maybe I won't. Okay, that's going to move the whole thing. Why is it down up there this time? All right, whatever. Here we go. So this is the piece of paper that I've given you. So to start our journey off, and I think we already did it just a tiny bit on Friday, we're going to talk about oxidation numbers. Oxidation numbers are essentially the charges that these things have, but they're a little bit different. Like in a polyatomic ion, we never found the charge of both the atoms. We just found the overall charge of the ion, right? In oxidation, when we do oxidation numbers, we're going to find the oxidation number of every single thing, and it relates to the charge, and most of the time it is exactly the same as the charge. You okay with that? All right, so let's start this adventure. So these rules will help us to determine these numbers and to do these things quickly. So to determine if an oxidation-reduction reaction has occurred, we assign an oxidation number to each element in a neutral compound or charged entity. So these rules, here we go. Elements in their elemental form have an oxidation number equal to 0. So just a simple reaction is like Na plus Cl2 goes to NaCl. This is a very simple redox reaction. So I'm going to apply these rules. Elements in their elemental form have an oxidation number equal to 0. So Na, just in elemental form as written here, has a little 0. That's its oxidation number. Chlorine, even though it's diatomic, it's still how it is found in nature. That's a 0. All right? But over here, we have Na with Cl. It is no longer in its elemental form. So we move to the next rule. It says the oxidation number of a monatomic ion is the same as its charge. Monatomic means it's not a polyatomic ion, which both of these are monatomic. So Na is typically a +1, Cl is typically a -1. And they will always be that way if they're just together. All right. Now, there's more rules. If you come down, it says nonmetals tend to have a negative oxidation number. That works. Although some are positive in certain compounds, and we'll work through one of those today also. This is a very important rule right here. Oxygen is a number 2 or a -2, except for in peroxide, and we don't do peroxide forever. So just go with the fact that oxygen is a -2. Hydrogen is a -1 when bonded to a metal, but a +1 when it's to a nonmetal. We're going to worry about the other half most of the time. All right, fluorine always has an oxidation of -1. The other halogens have an oxidation number of -1 when they are negative, but they can have positive oxidation numbers, however, most notably with oxyanions. Okay, so that's a lot to digest, but we'll work through each example. So in this example, what we did is we assigned the oxidation numbers, and we look up here. If something has changed charge, then a redox reaction has happened. So if you look, Na and Cl both changed charges, correct? All right. So what you would do next in these problems is you put a bracket connecting the things that changed. If you take chemistry in college, you'll do this the exact same way pretty much. All right, so you put little brackets to connect the things that changed, and then you have to remember the thing we're changing, I don't remember being blue, whatever. The thing that we're changing is a negative. So here we go. Na went from 0 to a +1. It became more positive, which means sodium lost 1 electron. And that means sodium was what? Reduced or oxidized? Oxidized, because Leo means lose electrons, oxidized. Which means the other one must have been reduced, right? So you look at chlorine, it went from 0 to a negative, so it became more negative. So it gained 1 electron. Now this I didn't balance it. This would be a 2-1. And you'll notice that really 2 NAs lost 1 electron. And 2 CLs gained 1 electron. These numbers will always be the same. This one, it was simple. They already were equal. But a lot of times, the loss and gain are not equal until after you balance. So that's a basic, very simple oxidation reduction. Now, this one is pretty simple. These two for right now, they are not redox reactions, so don't try and force them to be. But let's look at FeCl3 plus zinc goes to ZnCl2 plus Fe. So applying what I just learned, the first thing I should always do, what things get zeros? The lone elements. Now, I look at them in compounds. Iron over here is a +3 because of this. That number goes up there. Chlorine is a -1. Over here, what's zinc's charge typically? +2. Chlorine's a -1. So chlorine really, for oxidation reduction, has nothing to do with this problem, right? So now I connect my lines, or my things that change with the bracket. So Fe went from +3 to 0. 0 to a +2. All right. So look here. Iron became to negative, right? So it gained 3 electrons, which we would say it was reduced. It became more. So it lost. Go ahead. Say it out loud. Okay. Zinc, it became more positive, which means it lost 2 negatives, so it was oxidized. Now, do you notice the numbers are not the same this time? They have to be the same. So what have I forgotten to do? I got to balance. So if I see a 3 and 2, I should do the swamperoo. 2, 3, 3, 2. I hope they enjoy that video as much as I did. I guess it's supposed to be funny. But I didn't find it funny or inspirational to bring food. Maybe I'm a stooge. I used to be a fun teacher. Can you imagine? That was weird. All right, now, here we go. 2 and 3 do not equal each other. But if you'll look, this happens twice. So 2 gained 3, which really means 6, right? If you look at the zinc, 3 lost 2, that's 6. Be okay that those match up. Yeah, chlorine doesn't do anything, so it doesn't really matter. Okay, I'm going to erase this. Do you need me to keep it up there any longer? Okay. Number 2. Now, when I grabbed these examples, they were just off a worksheet that could be from any of the ones that we've done so far. So number 2 is not an oxidation reaction. Then the next thing I would check, are either one of these an acid? No, so it's not an acid-base reaction, which means I'm only left with what? A precipitate. So I would look at this problem. I would hopefully know by now NO3 is always soluble. So it won't be this. What's my precipitate then? AgOH. So all you would have to do here is go Ag plus OH minus goes to AgOH solid. Then you would be done. You all right with that? Now, I think it was this hour. Someone said, I don't really get why we use net ionic equations. Well, the net ionic equation is what is actually literally combining in the reaction. We don't need to worry about Na or NO3 because they didn't do anything at all before or after or during the reaction. Silver hooked up with OH and made silver hydroxide. Okay? Yep, it's the one that is not soluble or the one that is insoluble. Yes. All right, number 3. First thing here. By the way, let me write this in your notes if you're a note writer. Like almost every redox reaction will have at least one lone element. If it doesn't have a lone element, it probably is not a redox reaction. So you only have 4, right? You don't have 5 and 6. Is that correct? Oh, you do have them all? Okay. So these are the only 3 that will be redox. So number 3 then. Number 3, it's not redox. Do I have an acid? Yes. Do I have a red flag? No. So this is just a standard, and you can already see it's H2O and NH4Br. This is just a standard reaction where water sort of acts like a precipitate, where it's the liquid. So I end up with just H plus OH minus goes to HOH liquid. Now this one would be harder if I told you the states of these, because it is more complicated, but we're just going to go with that. Well, no, it's pretty simple. Sometimes you would need on the test if this was a solid or a liquid, but we'll just assume it's an aqueous. Okay, now number 4 though. Number 4, we are back to a redox reaction. So KClO3 goes to KCl plus O2. Mumble that a little bit louder. None of them ever change. That's what you think, but not true. We can still be friends though. First thing first, oxygen is always a what? When it's an element. When it's a 0, or when it's an element, it's always 0, right? Okay, now this part's easy. K is a +1, Cl is a -1. Because right now they are monatomic ions. All right, K, this is a monatomic ion, so it stays a +1. Oxygen, according to my rules, is always what? -2. But chlorine here, this one is not what you think it is. So please follow this idea. I'm going to write the chlorate ion. by itself. I know that chlorate adds to a -1, correct? Okay, I'm going to put a -2 up here. Now, please look at the screen, so hopefully this will click. You have 3 oxygens, and each is contributing -2 charge. So that's a net charge of -6. Are we okay with that? That means oxygen is forcing chlorine to do something it doesn't want to, but it can because oxygen is more electronegative. All right? Chlorine, what number -5 equals -1? It has to be a +5, which it is. Oxygen and fluorine can force any other nonmetal to do whatever they feel like. It's because they're the hottest ones. They're the most electronegative. They're the cool kids on the block. They're going to peer pressure chlorine into doing whatever they wanted to. All right. F will win that battle every time. Okay, so now I'm going to take all this stuff and move it a little bit out of the way. Okay, no I'm not, because it wouldn't let me. Why is this not working? Okay, fine, it won't work. All right. Has K done anything? No, but oxygen did, right? And chlorine, it won't let me move this stuff down here, but whatever, chlorine. So oxygen went from a -2 to a 0. So what happened there? Did it lose or gain? It lost 2. How did it become that? Because it was separated and then they didn't want to be separated, so they found each other. What post? But the thing we're losing and gaining is a negative. It's okay. It's confusing. You just got to be patient on this one because it is confusing. All right. A +5 goes to a -1. So chlorine definitely became more negative, which means it gained. And it gained 6 electrons, right? What? All right. So which one's oxidized? All right. Oxygen. Which one's reduced? Chlorine. This goes against most things. Oxygen usually wants to be reduced. So that would mean that this reaction is non-spontaneous. In order for this reaction to happen, we have to add a lot of heat, in case you care. All right. Now, we would balance this with the 2, a 3, sorry, a 2 and a 3, and then they would all equal each other again, by the way. All right. Kind of tricky, correct? When you have an oxyanion, that first nonmetal is going to be made positive. It will be forced to be positive because the oxygen is more electronegative than it is. Unless it's fluorine. But we don't have any FO3s. There's no polyatomic ions with fluorine. Because of that exact same reason. Fluorine is more electronegative. It's not going to have to share with anything. All right, you want to do one more? Because there isn't another one. If there's a lone element, it will be. Yeah. Anywhere. Either side. Yeah. It also is a redox. Okay. Here's another example. Just real fast. I don't even know why I teach anymore. All right, hydrogen's a +1. Here it's an element, so it's a 0. Magnesium is an element, so it's a 0. Over here it's a +2. Oxygen is always a what? -2. You all right with that? Phosphorus. Now, what I'm doing is actually a waste of time, but it's just to help reinforce this. PO4 adds to what? -3. Oxygen's a -2. What's 4 times -2? -8. What -8 equals a -3? A +5 again. So this is a +5. What would it be over here? Still a +5 because it's with phosphate. I didn't. I even said I'm doing this as a waste of time, except for to show you, once again, to work through this process. I, Tom Davidson, would never have messed with anything on phosphate. How come? Because it's together on both sides, so nothing would have changed. I was just showing you how to find the oxidation numbers of this middle nonmetal. Okay, so what did change? I'm going to back a lot of this out so there's room. All right, magnesium and hydrogen. If you ever have 2 different lone elements, you're already done. Like they're the ones that will change. Hydrogen went from +1 to 0, so it became closer to negative, which means it gained electrons, and it gained 1 here, right? Sort of. And then this one became more positive, so it lost 2 electrons. When you balance this out, you have 3 Mgs, so you better put a 3 right there, right? You have 2 PO4s, so you better put a 2 right there. That makes 6 H's, so you better put a 3 right there. When you balance all this out, they both equal 6 electrons transferred. There's a 1 here, by the way. How fun was that? Super fun. Okay. The one on the test is easier than this one. It's just like one of these first 2, either this one or that one. Yeah, Newman. No, because that wouldn't be its elemental form. It has to be how we would naturally find it, and that will always be neutral. So that would be a -2. Well, really, that's a super messed up question because it's a -1, but we're not going to stress about it. Okay, that's sort of your very brief introduction to oxidation numbers. We have an entire chapter dedicated to this later in the book. The last parts that we want to work on are what we call displacement reactions, which are what we just did. It's when you have a metal put into a solution and it produces a different metal and a different solution. So in this example, you had silver nitrate plus solid copper that produces solid silver and copper 2 nitrate. So in displacement reactions, ions oxidize an element. The ions then are reduced. You don't have to have this part super rock solid, so we'll go quick, but just look here. This oxidizes that metal. That metal is oxidized by that ion, or it is all right, it's a little tricky here because we have the thing being oxidized, which is the reducing agent, and the thing being reduced, which is the oxidizing agent. So, not too bad. Like, you don't have to have this, but you do need this thing right here. This is the most important part, actually, of the entire day. Well, not the day, but this piece so far. When we talk about these types of displacement reactions, we have what we call the activity series. You definitely should have read this already. If you haven't, you need to, because I'm not giving you a thorough explanation of all of this, because the book does. All right. The activity series says as you go higher up, the easier things are oxidized. So these, like lithium, would win the biggest loser competition. Gold, definitely not. All right. These things are oxidized easy. These things are oxidized hard. That's why my ring on my finger hasn't changed in 19 years. There are no elements up here that will react with gold. Gold wins. All right? So here we go. In order for a reaction to even happen, as written, the lone element must be higher on the activity series. All right? Than the one written as an ion. Now, whenever we talk about this, we're talking about the reactants. All right? So the reactants, the one that is alone, or your solid, must be located higher on the activity series than the one written as an ion. So since copper is written as a solid in this reaction, is above silver, which is written as an ion in this reaction over here, then this reaction will proceed forward. But if I took a solid piece of silver and put it in copper 2 sulfate, no reaction would happen because the lone element would be lower than the ion element, which would be copper. Okay, let's work through these examples quickly here. So I would not, on most of these, don't write out the equation. Identify the thing that is the solid metal, and then the ion. So in number 1, nickel metal. So is that a compound? No, it's just nickel. All right? So that's my lone element. So I'm going to put an L by that. Is added to a solution of copper 2 nitrate. I don't need to worry about this part. I just find the other metal. Copper is right here. And this is my ion. Is my loner higher on the chart than my ion? Yes. So will a reaction happen? Yes. Okay, now look at number 2 and number 4. It says hydrochloric acid is added to silver metal. It doesn't give you another atom. It gives you the loner, but it really is hydrochloric acid. That is hydrogen and chlorine. So really, this is saying your hydrogen or your H+. If it's an acid, if an acid is involved, then it's giving you this is the ion, hydrogen ion. Okay? So number 2 definitely does not react because your loner is silver. Your ion is hydrogen. It doesn't work if your loner is lower. Good job. Okay, try 3 and 4.
Nothing underneath hydrogen will react.
Correct. So with your lab partner, determine if number 3 and 4 will have a reaction. Time purposes. Chromium is my loner. Cobalt is my ion. My loner is higher than my ion, so yes. Correct? Number 4, calcium, that's my loner. It's put in an acid, so H is my ion. Is my loner higher than my ion? Yes, by a lot. That would mean this is definitely a very vigorous reaction. If you're asked one of these on the test, you will be given the activity series. Now, not every part of it, but you'll be given the pieces that you need to know for that part of the test. Are you okay with that? Okay, now, we are done with all the qualitative stuff for Chapter 4. The rest of the week is quantitative, all right? So as far as you're concerned, those top 4 things are the things we've learned so far for the test. Then ionic reactions, which include acids and bases, and gas-forming reactions, which are part of acids and bases. Number 3 are simple redox reactions, and 4 is the activity series. These top 2 are much more difficult. That's why we spent way more time on them, and they're much more important to your AP overall score than these are. So as far as what you care on the test, these are probably 40% of your score. These are probably 10, and the math is the other 50. You okay with that? Okay. So the math today is very simple. We're going to talk about molarity. If you're a note taker, put a big line, and then put like math or quantitative or stoichiometry or whatever, because everything from that line on is definitely going to be math-based. Molarity is a unit of concentration. In chemistry, we don't like the word concentration, so we use this little symbol of a bracket. The molarity, that unit, is equal to moles over 1 liter. All right? Typically in this class, I will give you the molarity. I won't ask you to calculate it. But you do need to know how to calculate it, just in case. So it shouldn't be that hard. Like I was up till midnight, but I wasn't. All right. If you're asked to calculate this, you'll typically be given grams that you need to convert to moles. So how do you convert grams to moles? It's really simple. You take your grams and you divide them by the molar mass of the substance. Yay. We can hear it in the background again. I don't know. Okay, so for instance, if you have 30 grams of LiF in 500 milliliters of water. So you take your 30 grams, you divide it by the mass of LiF, which is 17. I got those numbers from the periodic table. So I take 30 and I divide it by 26. And I don't know that answer. Let's just say it's like 1.08. You okay with that? $30 grams of LiF in 500 milliliters of water. The first step is to divide my mass by my given grams over the molar mass. So 30 over 26. I don't know the answer, but I just made it up as 1.08. But that's not everything, right? That's my moles. I now need to divide this volume, and the volume always has to be in liters. So I divide it by 0.5. Lithium fluoride. It's just a substance I made up off the periodic table. What's that? 2.16 moles per liter is the answer, yes. Lithium fluoride? Fluoride is 19, 2.16 moles per liter. What's that? All right, not that bad, right? Now, most of the time, like I said, I will just give you this number. And what's more important, what? I will give you molarity and volume and ask for moles. This is the way more important thing to be able to do. It's not that bad, but you must be able to do this. So if I told you you had 1.2 liters of a 2 molar solution, you have to be able to solve for moles. This is very simple. 1.2 liters. If I want moles, I got to get rid of liters, right? For every 1 liter, how many moles are there? 2. So I get 2.4 moles. So if I give you molarity and volume and ask for moles, multiply the two answers. Now, we must be a little bit more careful. If I told you it was this volume of 2 molar solution of MgCl2, this solution would have 2.4 moles of Mg plus 2. But how many moles would it have of Cl? 4.8 moles. The reason why is there are 2 chlorines that break off to every 1 Mg. So the chlorine must be 2 times greater than the Mg. Okay, the bell's about to ring. The very first of those 3 videos will cover this exact thing. Please watch them. You still have the worksheet that 3 total people out of 38 have turned in. 12 people have watched the first video out of 38.